In the last video, we got to the description of a system of linear equations in terms of a matrix, where the coefficients in front of the x, the y, and the z get fed into this new mathematical structure, this new matrix structure with rows and columns. And I want to go through some examples of doing that. So in this example, we have three equations and three unknowns, or our stack of three equations and our unknowns x, y, and z. Because there's three equations, when we convert into a matrix, there's going to be three rows. And because there's three variables, our coefficient matrix is going to have three columns. So our conversion process, I'm going to do it in columns because it's a little bit cleaner, I think. I'm going to put all the x coefficients in the first column. The first x coefficient, the number multiplying x in the first equation, is 1. And the second one, the second coefficient is -1 to make my ones non-fancy. And then the third is +2. Now I'm going to do the second column corresponding to the coefficients in front of y. First being -4, the second being +3, and the third being 0. If there's nothing there, then the coefficient is 0. And the last column, the z column, will have 3, -1, -4. Now I'm going to put a vertical bar that separates the left-hand side from the right-hand side, that denotes the equal sign that's there. And I put the numbers in the augmented part, 5, -3, 6. And I'll label it. We don't have to do this labeling, but I'll label it anyway. This is the coefficient matrix. And that part is the augmented part of the matrix. And this entire block is the representation of the SLE. This column is the x column, this is the y column, this is the z column. You don't need to label the x, the y, and the z. It's going to be implied by the order in which they appear. We have to make sure our system is in standard form before we do this, so that we can rely on this interpretation. Okay, here's a prime example for what we would have to do if the system of linear equations begins in non-standard form. I'm going to begin by putting it into standard form. So put into standard form. So the first equation, we have x1 minus 2x2 plus 3x3. Now I'm going to make a mistake here, but I'll come back and correct it. Equals 1. That's what it looks like we have. Now I'm going to do the second equation. We have x1, so adding x1 to both sides, plus x2 plus, there's no x3, so it's 0x3, and then a plus x4. No, not plus, minus x4. I have to subtract from both sides. Minus x4 equals 2. And now you see the mistake I made. Look at equation 1. I do not have anything in the x4 position. I have to go back and add in 0 times x4. We could have prevented this by looking ahead. By looking out, okay, let's look at what's the largest variable label that's there, and then kind of preloading our expectations. Saying, okay, we do have an x4 there, so I'm going to put a 0x4 right away. Or use pencil and just erase it and fix it. Okay, and then the last one, I'm going to add x1 to both sides, subtract x2 from both sides, x3 is already there, and subtract x4 from both sides, and there's nothing left on the right-hand side, so it's just 0. And I'm going to double check it, go back to the first equation. I subtracted, oh, I shouldn't have a 2x2 there, it's just x2. Good thing I checked. Minus x2 plus 3x3 plus 0x4 is equal to 1, and then added x1 to both sides. x2 is already there. There's 0x3, subtract x4 equals 2. That one looks good. And then add x1, subtract x2. x3 is already there. Subtract x4. There's nothing left, so equals 0. Great. So After you write it down, check it. I caught one fake mistake that I knew I was making, one real mistake that I actually made just from reading what was there. It's so simple to screw stuff up when there's this many pieces. Next, I'm going to convert into a matrix. So this converts as follows. We have 1, 1, 1 for the x's, for the x1s. We have -1, 1, -1 for the x2s. We have 3, 0, 1 for the x3s, and we have 0, -1, -1 for the x4s. I'm going to put a vertical line for the equal sign, and then 1, 2, 0. So that's taking that information and condensing it into a matrix form. I'm going to label these columns even though it's not necessary. Okay, we can also run this process in reverse. Given a matrix in augmented form, convert it to the corresponding system of equations. So this says the following. Actually, I'll do the labeling first. Notice that it doesn't tell us that they're called x and y. So we have to make up labels. We can use x1, x2, or x and y. Don't use a and b. It's a mistake to do that. Not a mistake. You will regret it. x1, x2, or x and y. Those are the two valid options. So row 1 says the following. Row 1 says that x plus 2y equals 3. Row 2 says that 4x plus 5y is equal to 6. Our SLE is x plus 2y is equal to 3, 4x plus 5y is equal to 6. This is just interpreting or converting back to the original SLE notation. So we can go forwards and we can go backwards. Why are we doing this? What is causing us to convert everything into a matrix when we already kind of know how to deal with a system of equations using those operations and using, substitution elimination? What's the driver for this? Well, all those operations that we did, swapping two equations, swapping the order, multiplying an equation by a constant, or taking one equation and multiplying or replacing it by itself, plus or minus a multiple of another equation, we can do all those same operations for an SLE written in matrix form and have a lot less writing to do. It also enforces a type of structure that will help us kind of guide our steps towards a solution. So it's going to look like trying to create a type of pattern inside the way that the numbers in the matrix appear. That pattern will guide us. That pattern will tell us if we're getting closer or further away from an answer. It's very helpful. It's totally worth doing this. It's totally worth learning all this in order to solve the system of equations. It's not a waste of time. We'll know that we're there. We will know that we have an answer, whether that's a unique solution, so just numbers for x, y, and z, or if there's a t, there's a family of solutions with a parameter, or if there's no solution at all. We'll know if we have arrived at one of those conclusions by the way that the system looks. So the way it looks will tell us when we can stop performing operations. There'll be a point at which it can be no longer simplified. And at that point, we'll say that the matrix is in reduced row echelon form. Like the example we did with the t. Can't take it any further, can't simplify it anymore. Once we get a matrix in reduced row echelon form, we can say that it either has a solution or it has a family of solutions. For no solution, we often and usually, do not have to bring the matrix all the way to reduced row echelon form. We can get it to a certain point and just say, aha, 0 equals 2, not true, no solution. Now, reduced row echelon form looks a particular way. It has this format that gives it away, if you will. I'm going to use this particular vocabulary that is not universal, but I think everyone who teaches Math 1229 uses this language, so I'll use it as well. We will know a matrix is in reduced row echelon form if the first non-zero number in every row is a 1. That does not mean that every row begins with a 1. Some rows will begin with a 0, but the first non-zero number has to be a 1. This is called a leading one. Next criteria for a matrix to be in reduced row echelon form, to be fully simplified, is every leading one that you look at owns its column without question. There are no other non-zero numbers inside that column where that leading one is living. It has no competitors in the column. Everything else is 0. So if we look at the example in the bottom right, that first top left number in that matrix, the first non-zero number in that row is a 1, as it has to be if this matrix is in reduced row echelon form, simplified form. And if you look below it, all the numbers in that first column are 0. There's no competitors. If there was a non-zero number inside that column below the leading one, then the system would not be reduced. The system would not be fully simplified. We would be able to go further, to get it more simple than the way it was written. Look at the leading one in the next row. The first non-zero number in that row is a 1. Above it and below it are zeros. So far, so good. And then the third and final row has a leading 1. Above it are all zeros, so it meets the criteria so far. Next criteria. The leftmost leading one is at the top of the matrix, and the rightmost leading one is at the bottom, and the other leading ones are in descending order depending on where they appear in a column. That means that the leading ones should form something that looks like a staircase, or kind of a staircase, going from the top left to the bottom right. If I was to change the order of row 1 and row 2, then that matrix would violate that staircase pattern, and it would officially not be in reduced row echelon form. So we do need that staircase pattern to be there. Finally, the last criteria for a matrix to be in reduced row echelon form is that if there is a row of all zeros, that row, or rather all such rows in the matrix, must be at the bottom. Got to be below all the other rows. This matrix shown here meets all these criteria. The first non-zero number in every row is a 1. Each of those ones, so-called leading ones, are the only non-zero numbers inside their column. And there's no row of zeros, but if there was, it would be at the bottom. So it has all the stuff we need. These numbers here, we can't do anything about them. We can't make the top right one go away without breaking something else, without making one of those earlier leading ones unhappy by putting non-zero numbers inside their columns. We'll often have to live with numbers elsewhere in the matrix that are not perfect, that aren't just ones and zeros. That's okay. A common question that is asked at this point would be, where's the right-hand side of the matrix? Why didn't you write in the augmented part? And it's just, I didn't write it, it's there. If we're talking about systems of equations, there is a right-hand side. All I'm drawing here is the coefficient part, the coefficient matrix. So here we have a set of matrices. Now we're asked which of the following matrices are fully in reduced row echelon form. We have to check the criteria, each of those criteria for each of these matrices. So I'm going to look at the first one. Matrix A has a leading one in the top left, and it's happy. I'm going to use happy. I'm going to say it's a leading one, and it's a happy leading one. What makes a happy leading one versus a non-happy leading one? If that leading one is in charge of its column completely. Everything else is 0. There's no other non-zero numbers in that column. So happy leading one, happy leading one. And there is no other leading one inside that inside that third row. That's okay. It's a row of all zeros and it's at the bottom. Those other numbers that are there, we can't do anything about them. We can't get rid of the 2, 2 and the 3, 1 without creating unhappy leading ones. This matrix meets all the criteria. Every non-zero row begins with a 1. Every so-called leading one has only zeros above and below it. The leftmost leading one is at the top, and then they descend in a staircase pattern going to the bottom right as we go down to the next leading ones, and rows of zeros have to be at the bottom. And that's it. That's the criteria. So it doesn't have to be perfect. It just has to meet that criteria. Next one, part B. So I'll put a yes here. All criteria are met. How about B? We got a top left leading one and it's happy, but look at the next leading one. This is a sad leading one. In row 2. It's sad because above it is not a 0. Above it is a non-zero number. Non-zero number in its column. This violates the requirement that one of the requirements for the matrix to be a reduced row echelon form. So the second one's a no, big no. Third one, leading one, zeros below and above. Second row, leading one, zeros below and above. And the third row, there's a leading one, zeros above and below. But one of the criteria is being violated, and that's the staircase. So no staircase pattern. So those two elements, they're in the wrong order. What we would have to do to fully simplify this is we would have to replace, or not replace, we have to swap the order of row 2 and row 3. How to fix the previous one, I didn't mention that. Well, we'd fix it by replacing row 1 with row 1 minus row 2. Then that would zero that number. It would be okay. So sometimes it's fixable. Actually, it's always fixable. And then the last one that's here, is that fully row reduced? Look at the criteria. We have a row that's first non-zero number is not a 1. First non-zero number in row 2 is not 1. So let's just go through a little bit more detail for each of those. I'm not going to read it. I just said all of this. A little bit cleaner, a little bit neater. Okay, now I'm going to show you how to use reduced row echelon form to solve a system of linear equations. But it's probably better to put that in the next video since this one is already almost 19 minutes long.